Hey guys, so here we are back in the scene shop. I'm going to try to make a video about the rigging stuff that would have been our next lesson. Yeah, this will be a lesson on the parts and fixtures that we use to rig flying scenery, as well as some other aspects of rigging and equipment that we use. You may remember some of you were building flats that were smaller parts of bigger pieces. Well, some of those pieces were actually part of, this is a fairly substantial piece of scenery, and the little flats that you built were just small parts of it that assembled together for the fly. So there's quite a bit to take into account when we want to fly a piece of scenery. From a safety standpoint and from an assembly standpoint. So we're going to go over a bit of that. First of all, we'll talk about the flat itself, and then we'll get into all these little pieces and parts. All right, so here we are back at the infamous chalkboard, and you may recollect my standard chicken scratch drawing of a standard flat, very similar to the ones that you've already built in the lab. The reason we're here looking at this is to refamiliarize you with the parts that make up a standard flat, and to discuss how we would need to change things, if need be, to make it fly. Remember, we've got our rails, which run the full width of the flat, the stiles that run up and down the length of it, which are smaller than the skin because of the thickness of the rails, and then the toggles that give us extra strength and more things to nail the skin to. This flat, if we were to take that flat, the question is, to fly it, where would you attach the rigging points? Would it make more sense to attach cables from the top, or down at the bottom, in which case the cables run all the way through it? Usually when I'm doing this class, somebody suggests that we have them up at the top, and there is a little bit of logic to that. Usually if you grab from the top, it's easier to make something hang straight up and down. However, that's the incorrect answer. And the reason being is we have built this flat, a standard flat, to do what? To sit on the stage or platforming. All of its engineering that goes into how we lay out these joints. There's a reason why the rail is the full width of the flat and the stile sits on top of it, is because this then sits on stage and there's no stress that is going to affect its overall strength. Everything is designed to sit. And it seems very simplistic, but there's actually logic that goes into this. Therefore, if we were to pick it from the top, what could very possibly happen, almost guaranteed would happen under what's called a shock load, is when you lift it, that you could rip the top out. And the heavier and more complex the flat is, the more likely that's going to happen. So if we were to fly a flat and we needed to rig it from the top for whatever reason, we would need to redesign how we frame it to make that piece up at the top, that top rail, strong enough that it can't just get torn out under a shock load. To eliminate the need to redesign our flats, all we need to do is pick it up from the bottom. By picking it up from the bottom, we're asking the flat to do exactly what it does when it's sitting out on stage, i.e. all of the weight is spread out and sitting down on that bottom rail, just as if it was sitting on the stage itself. So the cables run through it and attach here. I'll show you later pictures of actual flats, but in drawing, just so that you understand what's happening, the top rail, if we were looking at a top view of the flat, gets holes drilled in it, and the cable goes down through this. So you wouldn't actually see these cables here. Same thing with the toggles. So now every one of these supporting toggles is helping capture the cable. And then down at the bottom, we've got this pieces of hardware, which I'll be showing you shortly, that the cable's attached to. And they're attached to this rail in such a way that nothing breaks. All right, so the first piece of rigging hardware that we're going to look at is what we call a D-ring and a keeper plate. Very simple. Here's the D-ring, and this is the keeper plate. Starting here, just to show you the part that attaches directly to the flat. We talked about the holes that would drill through it. So if this was here our bottom rail, this would attach to the bottom rail with bolts, not screws, because screws can pull out, through bolts, nuts on the bottom, and attach. So we drill holes, bolt it on, and then this gives us a point to attach our remaining hardware to, eventually resulting in the cable that goes up and attaches to the batten that would fly it in and out. There's things that go in between those, but first we start with that keeper plate. All right, the next thing is the chain of adjustment pieces that we have before we go directly to the cable. So back at our drawing of the flat, if we just attach the cable directly to the keeper plate, what happens if we fly the flat in and we've made a slight miscalculation in our cables and it's at an angle? Yes, we usually have adjustment points up at the batten itself, lengths of chain that wrap around the batten, and then cables come off of the length of chain. But the trouble with that is to get at that, you either need to get 30 feet up in the air to make the adjustment and thus carry the weight of the flat, or you've got to fly everything back down so that the batten is at level, which means that now we're out of balance. Remember being out of balance with the curtains. And with scenery, that's even more delicate and sketchy in operation, so we don't do that. We make the adjustment point down here at the bottom of the flat. And so that's the next bunch of hardware that we're going to look at. Okay, so in addition to our keeper plate, which would be attached to our flat itself, we've got this other pile of stuff, and eventually we've got our cable. All of this goes in between. The first thing is this, which is called a trim chain. Very simple, a chain with a built-in hook. You can use something without the built-in hook. These are actually old school, and they don't really make them anymore, but they make life a little easier. So the first adjustment is this slides through our keeper plate and clips to itself in the middle, the D-ring. So now if our flat is out of tilt, by unclipping and reclipping in another position, we're moving it about a ½ inch every time. So that's one way, and that gives us a big adjustment. We could go up many, many lengths and change things dramatically. Another way we can use it is to attach directly with the hook, and you can flip this upside down too. And then the next point of attachment can adjust by which link it goes into on the chain. And obviously by doing that, if the cable's attached here and then we shift it here, it's essentially made the cable longer. We also have this. I don't know if anyone recognizes this piece of equipment. This is called a turnbuckle. It's an adjustable piece of equipment that goes between 2 points. In the case of our cable, it essentially makes our cable longer or shorter. These thread into what is essentially a interestingly shaped large double-sided nut with threads on it, and they thread into it or back out. And when you turn this one way, clockwise, it's tightening, clockwise. And when you turn it counterclockwise, it's loosening. And as it loosens, it makes the cable longer. And as it tightens, they come together and make the cable shorter. So that's our fine-tuning adjustment. It's very sensitive. You can get it absolutely just right by twisting that. You'll notice that this one has an unpainted side. Some of them are black. Oh, there's black on that side. And then it's gold on this side. We have ours set up painted yellow or gold, and that's always the top connecting point, and that way we have a consistent direction for tightening and loosening. If you don't have something to indicate it, it's easy to put some in one way and some the other way, and then when you go to adjust, you don't know whether to go clockwise or counterclockwise, lefty, righty, loosey, whatever. So that's it. So the entire assembly is set up easily by just undoing these rated bolts here. We connect the chain by putting the bolt through the chain, and again, we start with it in the middle usually, so that then if we need to make an adjustment, we can go either direction, but that's where we would attach that. This attaches here, that attaches to our flat. And now we have all the adjustment we need for fine-tuning things. So all of those various methods of adjusting the precise height of a flat on either side may seem like overkill. But imagine if a scene that's all hung on one batten. In this case, we've got 5 flats. This is our church scene here with 2 flats that sit on the stage with the arched doorways, a big rosette window, and then 2 cathedral windows. They all need to fly in. They all need to play at the correct height. And this is where all of that adjustment comes in handy, as we've increased the amount of weight hanging from the batten, so therefore we've increased the amount of counterweight, and therefore any attempt to adjust it up top at the batten is going to create all kinds of chaos with setting pieces on the stage, etc. So we need to, if we don't have our cable lengths exactly right down to the ½ inch, things will be tilted, and they also need to play with each other. These two need to land at exactly the same point. These should therefore be at the same height relative. You can see I didn't draw it quite right, but anyways, the complexity of all that adjustment starts to make sense when you realize how complex the adjustments sometimes need to be. Okay, so next we have a piece of 1/8 inch rigging cable. 1/8 inch is the diameter. It's made up of multiple strands of steel. I'm not sure how good that's going to focus, probably not that close. But anyways, this stuff, as skinny as it is very strong. It will in fact hold a static weight of 2,000 pounds without breaking a sweat. We rarely have anything that weighs that much. You'll remember that I've mentioned in the past many times Grauman's Chinese theater, which weighed a total of 1,500 pounds, but it had probably about 12 of these cables holding it. And it's not because the cable is the limiting factor, but by using the 1/8 inch cable, it's a great compromise between ridiculously over-redundant strength and yet being hard for the audience to see. Painted black like this, and it comes coated black. It's virtually impossible to see under most lighting from the distances we're at. You'll notice that there's this fitting going on here, and that's the important part, is this connection. This 2,000 pound rating is maintained if we have this type of connection at the end. And this would have been a very hands-on part of this lecture, because you guys would have had the opportunity to make this, as well as during the build of Spamalot itself. But There's this piece here that's called a thimble that protects the edges of the cable and also maintains a specific radius. Once the cable gets tighter than that radius, its rating is reduced. And that's something that you learn about tying with rope as well. But with this radius here, the rating isn't reduced. Also, this part here, it's called a swedge sleeve or a Nyco-press sleeve. Here's one that hasn't been crimped. You'll see it's oval shaped. It can allow the cable to go in one way, do a loop, and then come back the other way, and then it gets crimped in 3 places. Ooh, sorry, I'm not watching where the focus is here very well. It gets crimped in 3 places, and that, again, means that this connection is rated at the same 2,000 pounds as the cable itself. We haven't reduced the rating. Okay, so back to our hardware bits and bobs here, doohickeys or hoodinkies. Yes, so we've seen what the bottom attachment is with all of this pile of stuff. Up at the top of our cable, we would be going around a pipe, but the cable doesn't go around the pipe usually. What we use instead are pre-cut sections of chain. I have these in what we call a 1 wrap. It's about 11 inches. It makes it around a batten. And then you use this lovely guy here, which is called a quick link, to complete your connection. It goes through the chain. You can go through at either end. You can fit it through the middle, again, to give you adjustability. And then it obviously attaches to our cable. When it's hanging, you want it like this. This is the part going down. The chain is going up. So first we need to go into our chain. The chain is going up to the pipe, the batten. The cable is going down to the scenery. And you'll notice that the nut is up at the top of this, and that's a little bit important because we don't want that to come loose. These get tightened only hand tight. We don't use a wrench. Over tightening can damage the threads, etc., and this is a reusable part. And so therefore we want gravity to make sure that it's not helping open it, so we hang these in the correct direction. And so that's called a quick link. A maillon rapide in French. Don't ask me why I know that. I believe they were invented by a Frenchman, but I could be making that up. So that's that connection. The quick link is the one that we use the most because they're very strong. They have a very high rating. I believe that this one is rated for about 5,000 pounds, as is this chain. So it's not going to break, simply not going to break under the loads that we have here in the feeder. And they're cheap. Often a better tool for certain types of rigging is this lovely item here. And this is a huge one, which shows up better, for example. This is called a screw pin anchor shackle, or shackle. There's different types, this being the screw pin type. It's a pin with threads for screwing. Anyways, this has a massive rating, and they get used in a specific way. You want it to pull this way, but this arc means that you can bridle and have 2, 3, or more cables so long as they're spreading out evenly coming from it, and then one connection here. This is a little closer to the size that we'd use, but actually we often use much smaller ones. This one here is rated for about what our cable is. But there are times where we need these big ones, span sets, etc. Another giant quick link for demonstration purposes. We don't usually need one that big. And over here I've got these guys. You probably recognize these as carabiners. That's not a carabiner. Most of these are real. One of them is a fake right now for some bizarre reason, and actually for the past 15 years or so, fake carabiners have been a thing to put on key rings and whatnot. So just make sure that when you're actually rigging overhead or technical climbing, which is what they were really made for, that you're using the real thing. This here, of course, is the toy. Fortunately, this one actually says not for climbing on it, but a lot of them won't say that. The real thing can hold a lot, at least 2 people's worth of weight. And I actually don't remember what the ratings of these are. They're all similar except for this bad boy, this bad Larry. This is a rescue carabiner. If we were here in person, you'd feel how light these are. For climbing in the mountains, you want something super lightweight. You're going to be carrying many of these, maybe a dozen or more. And they weigh next to nothing. They're made of aluminum, very lightweight alloy. This is made of steel. And as a rescue carabiner, it doesn't need to be super lightweight. It needs to be industrial strength strong, and it's got an auto lock feature. This locks automatically so that it cannot be accidentally opened when you're rigging somebody's tray to the helicopter line or whatever. And this can hold a whole lot more weight than these. We use these in rigging in the theater, not in Will's stage so much, but over in Jay's studio where we have to do a different type of rigging fairly regularly. We had to do some for A Brief History to make that flag fly. Very lightweight rigging. These were involved. Another part that was involved were the pulleys. Your standard hardware pulley that you get at a hardware store can be used, but it's both inconvenient and it's not rated very high. They're inconvenient in that you need to feed your rope through, that's the real inconvenient part. Also, they tend to have attachment points that you need to have a very specific size. So if I wanted to attach this to something, I can't use this carabiner because it's too big to fit through there. But I could use this one. Most of these, sorry, I said carabiners, shackles. These carabiners won't work at all. It won't fit on. So that becomes a problem. And again, having to always run your rope through it is a problem. If you've already started a setup and realize you needed to add a pulley in the middle, you'll have to pull your rope all the way back through. And in some cases, that can be hundreds of feet of rope. So I use, once again, climbing hardware. These are very lightweight to feel. They hold a good amount of weight. But being designed for technical climbing, the carabiners slop right into them. Then I can hook this onto a piece of the J Studio grid, and they open. So I can just open it, put the rope in there, close it. So if I've already got my rope run and I want to change its direction or alter, add more, or remove pulleys, it's very easily done. They're great for working. I have slightly heavier duty ones for heavier rope, but they work the same way. Another type of pulley is this one we see here, which is designed for giving a mechanical advantage. You'd have your rope loop up and down. It's called a block and tackle. And that's what this little piece off the bottom is called a becket. However, I use this often for rigging, not for heavy lifting, but for just rigging something that needs 2 points. Rather than having 2 separate pulleys, I'll have one of these. The becket can often help. I can pull on that and attach that to something, as well as obviously have the weight being attached there to keep it from twisting and binding. 2 ropes would go through, and then they'd drop down to something like the American flag in Brief History. It needed 2 points, obviously, to lift it up. The flag was attached to a pipe. I needed at least 2 points. To make sure that those ropes go together at the same rate, the two ropes going through and attaching to the pipe that the flag is, we use a thing called a clew. This is a clew. This is, in fact, the exact clew that was used for the flag in brief history. So we'd attach one rope here, and in this case, I can attach 3 different ropes here. We only needed 2, and those ropes went off. I say rope. It was a heavy-duty line that we call tie line, just this black line, and that was used to raise the flag. On this end was, in fact, a piece of rope, because that was something that a crew member had to pull on to lift it up and let it down. It didn't weigh much, but you want a piece of rope to pull on. So that's a clew. There's a couple more little doohickeys. This is just a swivel attachment. Sometimes you need to make sure that whatever you're rigging can swivel. So you can put that in line with a carabiner, a small shackle, or our trusted quick link. This one's too big, but another guy is this thing here. This is called a grip lock. This is it's new relatively compared to everything else that we've seen here, which has been around for years. This is something that comes in very handy for rigging in J Studio. It's basically an adjustable version of this connection. Now, I say that, it doesn't have the rating that this does. Remember, the 2,000 pound rating is maintained. This drops the rating down to about 500 pounds. But for most of what we do, that's more than enough. And the way this works is there's a sort of clamping mechanism in here that works to grab the cable. The type of mechanism is referred to as a collet. And as we screw this up here, it tightens that collet down. There's probably 3 or 4 prongs that end up squishing down to grip that cable. And then once it's tight, it can't come undone. Well, like I said, it's rated at about 500 pounds. A note on ratings. We say 2,000 pounds, 500 pounds. Those ratings are the rated static load. And if they meet specific, if they meet specific standards, that means that the testing methodology to arrive at that number has put the breaking point at between 3 and 5 times the rating. Usually it's at least 4. So that means that when they say that this cable is rated for 2,000 pounds, they applied a constantly increasing pressure, slowly, not a shock load, but slowly increasing the pressure with a machine that's very powerful until it broke. And it broke fairly consistently at about 8,000 pounds, or 4 times what that rating was, which is an interesting thing. So this, which claims a 500 rating, it means that it probably slipped at about the 2,000 pound point. I would never push the rating. I go with the rating, but it's just something to know. When you go into an elevator and it gives that capacity, the smallest part, the weakest part, is probably rated 3 times what they're saying is allowable in that elevator, for example. So it's just a little something to know that those ratings are not right at the edge. And part of the reason is that thing that I've been mentioning, the shock load. Shock loads increase the stress on the cable by multiples. So a static load, if I just hung 2,000 pounds from this, there's 2,000 pounds of pressure. If, however, I had 2,000 pounds and was swinging it around on the end of a crane, or we were using our fly system, and something slipped and it did a bit of a free fall and then stopped, that's the shock load. And all of a sudden that, depending on how far it fell before it stopped, etc., the 2,000 pounds of force gets multiplied pretty dramatically, and that's when things tend to fail. So again, part of the reason why we're very comfortable using this heavy stuff that's rated so high is to help cover us in case of some sort of an accident that allows something to go into a shock load, and we're covered. Shock loads, kinetic loads, weights, ratings. We're back to the math part of the job of technical theater. I'm not going to get into much of it right now, but there's calculations that go into the safety of working with that system. And again, you saw when we were working with the curtains, those soft curtains, how much they ended up weighing and how careful we need to be in calculating weight. And the same thing goes into scenery. It becomes even more important because getting hit by a piece of scenery would hurt a whole lot more than getting hit by a curtain. Anyways, yes, so math everywhere in technical theater. Something you got to get used to.